All right. After having developed the full model for the MOSFETs and bipolars, now we've gone through a phase that we've understood the basic model. Now, what we did was not a complete and thorough analysis of all the nuances of the device, because this is not a device physics class. But we did sufficiently to understand the core concepts that would be enabling us to go forward. Now, the next thing really is to start moving from the devices to the circuits. And one of the things that you will see is that in many case scenarios, in fact, the exact dependence of the current and voltage, exact relationship, in many cases actually does not matter. There are cases where it does matter, and it's important to understand it. But in many other cases, the way we analyze it, we will see that as long as you have a certain kind of behavior, the exact analytical relationship, whether it's like exactly quadratic or some other function, may not matter as much as we may think in many of our cases. And there are some cases that it does matter. So we try to understand it. And you will see that there's a unifying picture that captures essentially all of these three-terminal devices. As a matter of fact, one of your problems said, we've asked you to do this for a vacuum tube, which initially may sound very passé, but nowadays people are talking about making the next generation of the fastest transistor with vacuum tubes, because then you don't have the atoms getting in the way anyway. So you can make three-terminal devices. So you can see what these things are. And that picture, part of that picture, that bigger picture of the unifying framework, is what we call the small signal model. Now, what is a small signal model? So a small signal model is an important part of the analysis and design of the circuit. And what it is, really, before we get into the nitty-gritty of it, is a linearized perturbation model. So if you come back from a physics background, see that if you have a generally nonlinear behavior, if you look at a certain point of operation in that picture of the nonlinear characteristic, in a near vicinity of that point, you can actually linearize it and deal with that linearization as a perturbation on top of your general behavior, and that perturbation analysis makes it easy. So now, the reason that is useful is that it opens up all of the circuit analysis to the linear circuit analysis techniques, such as nodal analysis and things of that sort, that we have discussed. You probably have seen it before, and I will quickly review. We'll quickly review later on, just to make sure that everyone's on the same page. So all of those theorems, all of those things will become applicable. Now, if you have a nonlinear system, then you need to really kind of like come up with other things. And there are other techniques that we deal with. We deal with nonlinear systems as we go forward, but only when we need to. So let's go back and actually do this, and refreshing your memory in terms of the transistor. So what we will try to do today is to develop the small signal model for the BJT and MOSFET side by side. So we'll do a parallel analysis. So everything we do for one, we'll do it for the other one. And what that does, it allows you to see the similarities and the differences as we go, and see what are the commonalities and what are the things that are always repeated and what are the things that are different. So we're going to have a dividing line here. And maybe I can just get rid of this title now that everyone knows. So this is the BJT side, and this is the MOSFET side. And you can do it for JFET, you can do it for MESFET, you can do it for vacuum tube, you can do it for any kind of device that you have. But we will do two to see the difference. So let's start with the basics of the operation of the transistor. So a transistor, the picture that we developed, was something like this. An NPN, for example, was an N plus PN. Well, there was an N plus for contact, but let's make it simple. So this was the three terminals of these were the three terminals. Well, let me just do it the other way around. So this way. So this was the emitter, this was the base, and this was the collector. And which way was the current flowing in these things? You remember, it was you're injecting electrons from the emitter, or emitting electrons from the emitter, passing through. Most of them make it to the collector if you have the right operation, if you're in the forward active region. So this is also forward active region, remember, FAR. So in that region, you have electrons being injected, which means that the net current, because electrons are negatively charged, is going this way from the outside perspective. And that means that the electrons are going, the charge is going this way. So there's a current IC there's a current IE, and then there's a current IB. And of course, we know that IB plus IE equals IC. Now, this is generally true. Now, why is this generally true for typical devices that we have? KCL, right? You said KCL. That's correct. But is it true at very high frequencies too? For example, if you're switching the transistor quite fast, would you expect this expression to hold still? Well, how fast is the question? So let me ask you this question. So your answer is correct. Some people were shaking their head and said, no, yes, at some frequency this will not hold because there will be some lag and delay between these things. But how high is that frequency? For this to fail, KCL has to fail, right? And for KCL to fail, there is something that needs to fail. There's a condition that needs to hold. So this should not be a lumped circuit anymore. So for this to fail, the dimensions of this guy should be comparable to what? The wavelengths of interest, right? And for that to happen, so these transistors are not really that large, presumably, right? Especially if you're talking about integrated transistors, you're talking about microns. So this will fail at optical frequencies for a micron level transistor or submicron level transistor, or submicron level actually today. Now, which basically means, and at that point, these transistors are generally not very useful as a transistor, which means that this always holds as far as we are concerned. So the correct answer is that this doesn't always hold, but for everything that we are practically interested in, this does. Now, if you are in a situation that you have a relatively large structure made out of these transistors, and you're operating at hundreds of gigahertz or terahertz or something like that, you may want to think about that, but usually it's the interconnect that becomes more important before this becomes important. So this is a pretty good assumption. That's what my point is. Okay, so that's one thing we know. What else so this is the device physics picture of this thing, right? But we have a symbol for this device. It's a transistor, and the symbol looks like this, right? As you're probably familiar, C and E, the collector, base, and emitter. Well, let me write this capital because we saved the lowercase and uppercase for different things. So I should have done this also in capital. Capital C, capital D, and capital E. Okay. Now, by the way, do you know where this symbol comes from? Does anyone know? Does anyone have a guess? You remember when I drew the first transistor, the one that was done in Bell Labs, the point contact transistor at Bell Labs? You remember how I told you it was made? They made a wedge, right? And they put some conductor on it. And they cut this wedge, the tip of this wedge, and they put it on top of this substrate. It's easier to move the substrate now. Right? What does that look like? Turn it 90 degrees. It's that thing. And the symbol, by the way, the other thing about the symbol is that you differentiate the NPN and PNP by the direction of the arrow. The arrow is always on the emitter. And the arrow basically coming out implies that this diode is pointing this way. And the arrow going in, which is the case of the PNP, means that this diode is pointing this way. So those are the mnemonic devices, really, if you will, or quote-unquote mnemonic devices, to help you understand what that is. But so that's the big picture. Anyway, that's a historical aspect of it. So we'll get to the PNP again. So that's the transistor. So you have the IC flowing here. You have the IE and IB flowing this way. So your current, you have current going into the collector, and you have current going into the base and coming out of the emitter. Again, this is review for many of you, but just make sure that we are on the same page so there's nothing missing. So, and then we have a PMP, right? Which is the counterpart of this thing, where you have a P plus you have an N, and you have a P, and the symbol for it looks like this. So here you have holes being emitted from the emitter. So holes are going this way. Most of them in forward active region make it to the collector. So you have a current going this way, that is IE. You have a current coming this way, which is IB, and you have a current going this way, IC. So this would be IE, IB, and IC. The direction of that arrow also points the direction of the current flow, the way it's drawn. So it's helpful in that sense. Now, why do you think I did this PMP one backward? So this is emitter-based collector, and that was collector-based emitter. I did it upside down, really, right? Why did I do that? Is there a particular reason that we did this, or so that the current is also flowing down? So there are some unwritten rules, and we'll talk about this more when we do more circuits, about the way you draw circuits. Now, circuits are really topologies, right? And we refer to them as circuit topologies, meaning that it's the way they're connected that matters. It doesn't matter where things are. I mean, I can take 5 transistors and put them in different orientation. Presumably, if I have a circuit doing something, if I make it upside down, it should not change what it does. Or if I take one of the transistors and twist it, as long as I don't make it disconnected or something like that, it should still operate the same way, right? So as in that format, they are topologies, so it doesn't matter. But there's something that makes understanding and designing and reading circuits a lot easier, which is that trying to keep the higher potential higher on the schematic and lower potentials lower. So if I'm drawing a circuit on the whiteboard, the higher potentials would be relatively higher, drawn at the higher points, the higher elevations, and lower potential will be drawn at the lower elevation. And you can draw the same circuit many different ways, and I can take the same circuit and make it very complicated and impossible, very difficult to understand. As an interesting aside, when I was in grad school, there were this group of people who were trying to do circuit design by genetic algorithms. So they had these constraints, and also so they came up with this circuit, and so they had these circuits that said, oh, look, you know what, our computer design, and this circuit like had 220 transistors or 200 plus transistors, right? So, and everybody was looking at it, and this is not drawn by a human being, right? So these transistors are in just a random orientation, etc. So everyone said, okay, but this must be great. We don't know. Right? Nobody can nobody can analyze this. So I said, let me see. So I took the schematics were 2 sheets, not 1 sheet. I mean, it wouldn't fit on 1 sheet. So there were 2 sheets of schematics. I looked at them. So this transistor is off. This one's off. This one's off. This one's off. This one's off. This one. So I went through all of them. So out of the 200, let's say 200, if it's more than 200, 196 of them were off. And there were 4 transistors. 2 of them had formed a basic cascade, which we'll talk about. And the other 2 were 2 diodes shorting the supply to ground. I said, wait a second, this doesn't make sense, because then the current consumption, where are the specs they achieve? And sure enough, there was no power consumption spec on it. I said, have you checked the power? And they went back and said, yeah, it looks like a milliwatt something. I said, are you sure it's a milli, not a mega? I said, oh, yes, it's mega. So, well, of course, circuit schematics, circuit drawings, circuit simulators would give you mega amps. Of course, you won't have mega. So the point of this story is that the way you draw a circuit will have a significant impact on how much you can track it. So we haven't gotten into it, but we'll see. So anyway, so that's why they're upside down. So we haven't even started with that. So let's do the similar thing for MOSFET. So MOSFET, how does it look? And again, we have 2 types. We have the NFET, which is basically N plus P, right? And you can draw it this way. Now, the way NMOSs are made, generally speaking, not always, but often, they are made symmetrically. So you can actually switch the 2 terminals. But at any given point in time, there is a certain direction of current flow. And for that direction of current flow, you have current going into the drain, coming out of the source, and then you have the gate, which I didn't show here in this picture. Right? This is the gate. So this is the gate. And there is, again, according to the classical model for MOSFET, what is the gate current? At least the static or DC gate current. It's 0, right? But so this is IG equals 0 for classical model. But again, if you have a gate that's 3 atoms thick, you can actually have tunneling current. So you can have a current for very small MOSFET transistors. Right now, we are dealing with a basic model, so this is the way it looks like. And of course, if you have so that's an NFET, your NMOS, and then this is going to be, and this is where they were NPN and PNP. And then you have the complementary one, which would be P plus with the gate. And then here you have the arrow going in. So what happens is that you have now again the current, so this is IS, this is ID, and well, this is IG, which is going to be 0. So you can see the parallel, right? I mean, you can see the NMOS and NPN have the same flow of current, and PMOS and PFET have the same flow of current. Okay, fine. So this is the basic drawing. So what were the general governing equations describing this device? Right? So the basic equation was that IC was IS e to the VBE over VT. And then if you wanted to take the early effect into account, it's VCE over VA, something like that. And also the other thing that we knew is that, again, all of this is in forward active region. IC was going to be beta IB. So these were the two equations governing. You can see that the primary dependence, even if you ignore this one, is the dependence of the collector current on the VBE, the base emitter voltage, which is an exponential dependence. So if you think about it, this current is controlled by this voltage. You can also think about it as, the collector current being proportional to the base current. But if usually you need to generate this base current somehow, right? Or the voltage. So the question is that, is this a current-controlled current source, or is this a voltage-controlled current source? So let me pose that question to you. Is this a current-controlled current source or voltage-controlled current? Yes?
I mean, you could model it as either one.
Right. You can model it as either one. Yes. You can model it as either one. So which one would you pick? Well, it depends on what you're driving it with. More precisely, or more accurately, the way to think about it, and we'll see this is a recurring theme, whether something is a current-driven or voltage drive or current drive is a relative matter. What really matters is the impedances, the drive impedances, level of the impedances, and what the driving point impedance is, the impedance of what you're driving. So if you are driving a high impedance, generally speaking, and we'll see this again in many different scenarios, if you drive a high impedance, you are driving a voltage. So you're showing, it's a voltage sensor. It's something that measures the voltage. If you're driving a low impedance, it's easier to model it as a current sensor, something where you put the current in and you measure it. The same thing on the driver. What drives something, if it has a low source impedance, it's better to model it as a voltage source. If it has a high source impedance, it's easier and more accurate, more intuitive, and it would result to more intuitive results if you view it as a current source. So there's nothing magical. There's no transition point that, oh, okay, all of a sudden this becomes voltage source or current source. It's just a matter of the impedances. If people talk about current drive, voltage drive, et cetera, I think the better way of talking about is a low impedance drive, high impedance drive, low impedance sensing, high impedance sensing. So it makes sense that way, I think, better. Anyway, so that's the equation governing this. And let's go through this a little bit more. So what does this mean? It means that if you take a transistor, you have to make sure, first of all, this only holds in the forward active region. So for the transistor to be in forward active region, what is the condition for being in forward active region? Is that this junction needs to be forward biased and this junction needs to be reverse biased. In other words, this voltage cannot be lower than 0.2 volts or something like that. But once you get to 0.2 volts, you're basically starting to forward bias this junction, and you have basically, you're leaving the forward active region, so this doesn't even hold anymore because of all the interesting things we talked about that happens in the device physics that we'll come to from time to time. So let's say now you're in this situation, and then you have a voltage, right? So you can have, let's say, a VBE. Let's show it as a source V, capital V with lowercase b. So the way the notation we use here is that we use the capital combined with lowercase to show everything. We show, if you use all capitals, it means that it's just the DC. And if you show all lower cases, it means that fluctuations or perturbations that we're going to be talking about. So that's the notation. So this basically, a little bit of this, a little bit of that means that everything, to me. Some books use a different combination. So let's say you apply some collector voltage. So let's say you just bias some voltage to the collector. There's no resistance here for now. And then as a result, there's going to be some current, IC. Because now if this voltage is sufficiently large, this junction will be reverse biased, this junction is forward biased if you have sufficiently large voltage here. So you have this exponential dependence. So the key question, the most important behavior of this transistor is coming from what? If you look at this exponential behavior, if you look at, forget about this part for now. Just let's focus on the most basic part of it. This is an exponential. We said this looks like an exponential, right? And as such, if I've set up my VBE to have some DC value, okay? Let's call that V capital BE. We sometimes call this the quiescent up point or the bias point. And then that corresponds to some IC. Sometimes you show it like VBQ, VIC, but just anyway. So this is the operation point. This is what we call bias point, where we have set it up. So now the other thing is that now if you apply a perturbation on top of this, so let's say this is the VBE, lowercase VB, the perturbation on top of that, this would produce a perturbation, right, on the current. So if I map this here, and this is not a linear dependence, you will see something that looks like that. So your current is changing in response to your voltage. Now, of course, how much it changes, it depends. This ratio depends on where you are, correct? It depends on your operation point. If I move, instead of being here, if I were here, I have a smaller slope. What I'm really looking at is the slope of this line. Do you agree? What determines this transition is the tangent at this point. And the slope of this line has a name. We call it transconductance. Because it has units of conductance, because it's a current over voltage, but it is it's the ratio of a current of a different port with respect to the voltage of a different port, and hence the trans part of it. So it's a transconductance, and we show it as GM. So the slope of this line is GM. Now, if you want to calculate it, you can easily see GM, as we defined it by definition, is DIC dVBE. Right? Which, from this expression, if you ignore this part, what do you get? If you differentiate this with respect to VBE, what is the derivative? It would be itself times 1 over VT, right? It would be this thing times 1 over VT. So you can actually easily see it's basically IC over VT, where VT is KT over Q, which is 25.8 millivolts at room temperature, let's say roughly 25 millivolts. 25 millivolts at room temperature, roughly. I mean, it's a little bit less. It's a little bit more than that. So now, and you can see, this is also a good number to remember because we'll use it a lot. Again, this is that for 1 milliamp, what is your GM? If your current is 1 milliamp, so your operation current is 1 milliamp, it's 1 milliamp divided by 25 millivolts, so it's 1 over 25, so it's 40 millisiemens. So at IC equals 1 milliamp, this is GM is roughly 40 millivolts. We also use the inverse of GM, which is we call RM. So 1 over RM defines that, and then basically that makes RM 25 ohms. So this is a good number to remember. At 1 milliamp, 40 millisiemens, and or 25 ohms. right? So because if you say that, okay, I'm designing something for some, I need the GM of 4 millisiemens, then you know that you're going to be operating at 100 microamps. If you say, oh, this transistor is running at 10 microamps or 1 microamp, then you know you're at 40 microsiemens. So you can scale it up and down. It's a good number. This is also a useful number. So RM and GM. This is the most important part of the transistor. This is essentially the transisting part of the transistor. Everything else that we develop is parasitic. Everything else, and there's a lot of them, but everything else that we deal with are bad stuff. This is the good part. Everything else are things that you'd prefer not to have if you could avoid. So I want to be clear about that because that's important. Now, let's do a similar thing for the MOSFET, right? I mean, these are, again, review, probably for many of you. But let's do it. Oh, before I do it for the MOSFET, the same thing the similar thing would happen for PMP. The way it would look like is that you would be operating at VCC, and a lot of times going forward, we may not draw the battery anymore. So what you will see, so let's start doing it now. You will see this. This means sometimes we call these rails because sometimes we draw them across. They look like rails, and sometimes you say rail-to-rail swing. It means that going from the highest potential to the lowest potential of vice. So some of this terminology I just want to kind of familiarize you with if you're not familiar. So this is a rail, and then you basically have a VEB here, and then you have a current IC. In this case, we can connect it to ground and like that. And VB. So sometimes we may actually show something like this. This implies that there's a battery or some voltage source of that source there. So if you show it this way, that implication is there. So there would be some shorthand going forward. And if you're uncomfortable with any of them or if something doesn't make sense, just feel free to stop me and ask, please. Because otherwise it becomes very incomprehensible pretty soon. Okay, so that's for the bipolar. So how about the MOSFET? Again, let's go through the equations for the MOSFET. The equation, the primary, if you are in the quadratic mode of operation, again, this is for pinch-off region. We're going to talk about pinch-off region. Now, what is the condition for pinch-off region? If you remember, there are two conditions. VGS is greater than VT for the transistor to be on to begin with, and then VGS minus VT being smaller than VDS. Now, this VT has nothing to do with this VT. It's just bad notation. Now, VTH doesn't help either because this is threshold and that's thermal. So we just know if you're talking about a MOSFET, VT means the threshold voltage that's adjusted by the implant charge and the flat band energy, the differences of the work functions, things of that sort. And if you're talking about a bipolar, we are talking about something that's related to fundamental constant and temperatures. Boltzmann constants and electronic charge and the absolute temperature. We can try to avoid this, but now there's a parameter. You can see that this parameter is a recurring parameter, right? VGS minus VT. You've seen it several times. I mean, a lot of things because it determines the conversion charge, etc. So this actually sometimes we use a specialized symbol for it. We call it delta VGS, and it's called gate overdrive. So it's basically the excess over VT. And if you think about this strong inversion model, it's this excess over VT that produces the channel charge, if you ignore the weak inversion or the subthreshold current. Okay? So these are, again, basic stuff, just making sure everyone is on the same page. So in pinch-off, the current of the transistor is given by what? We derive these equations, mu n Cox over 2, W over L. Now, and I will talk about W over L again quickly. VGS minus VT squared, and if you want to take the channel length modulation into account, lambda VDS, or you could write it as VDS over VA, some early voltage. So you can like lambda is 1 over VA. And now, what do we mean by W over L? We've talked about this again, but just this is an important parameter in the design as we go forward. What do we mean by W over L? Well, if you remember the three-dimensional picture of this transistor, right? If you look at this three-dimensionally, So let's see, this is the gate, something like that, right? This is the L, the channel length, and this is the W. Now, the way you do the transistor in a layout, when you are making a transistor in a layout, you're looking at a top-down view. So the transistor will look like this. Well, just drew it poorly, but. So this is the way the transistor will look like when you draw it, when you do a layout, which basically means that this is the source, this is the top-down view, right? And this is the gate. You may say, well, wait a second, why is this line going through here? Why didn't you draw it this way? First of all, drawing it that way is harder. But more importantly, the way the transistor is built is that there are these different masks, and we'll talk about that. You will see that as we'll discuss slightly later. But these masks, so you basically use the gate. Often the gate is used as a mask for making of the drain and source. So whatever you do to the implant that you do to make the drain and source a high density, you do it to the gate too, but the gate blocks it. So effectively, these parts don't get the same doping that these guys get. But practically, the mask looks like that. So the transistor in the layout looks like that. And the BJT in the layout, by the way, which I should have done, I forgot, looks like this. So this is the emitter, this is the base, red is the base, and this is the collector. And the side view of that, if you look at it, is something like this. Again, this is simplified. We'll talk about the more detailed version of this later. But so this is your N plus, this is your P, and this is your N. And there's, of course, we said we needed some N plus here, so there's an N plus here to make the contact better, but this is N. And this is your P. Now, of course, these need to have contacts. So what you may see on top of that, you may see these X's, which is where you make connections to these transistors. And the same thing here. You will have a contact here, you will have a contact here, and you will have probably a contact here to make connections to these three terminals. Now, are these pictures clear? So if I do a cross-section of this, the side view of this too, just so that you can see, looks like that. So top view, side view, top view, side view of the transistor, the way they are made. Okay, so how about, so this expression was what we saw. This is the classical quadratic long channel model. And we saw that if you are short channel, what you have is that, so in the short channel case, so let's, or velocity saturated case more accurately, velocity saturated, then you have an ID that's basically mu n Cox over 2 W E sat, VGS minus VT. We get a more linear behavior. And these are both in the pinch-off region, just pinch-off velocity saturated or not velocity saturated. And of course, we knew about both of them that this VA, or that's what over lambda, we had a definition of it. This is getting pretty crowded here, but I'm going to just write it. Let me just at least write it with a different color. And VA was defined as IC over DIC dVCE. And here, VA is defined, or 1 over lambda is defined as, again, ID dID over dV ds, drain source. Okay. So these are the basic equations describing this. So, and again, if you want to come up with a similar treatment as this one, you have to bias your transistor. So you bias your transistor in a certain way. You basically say, I have an NMOS. I apply some VGS here. I apply a VDD. And I monitor my drain current, ID, versus this VGS. And we plot that. And depending on what kind of behavior you have, so you have a VGS and you have an ID here. So it's either quadratic, or it could be linear, or something in between. So you have something like that, and it doesn't really matter which kind it is. So again, you have an operation point. You have some VGS that corresponds to some ID. You have some fluctuation, some perturbation on top of that. That would produce some perturbation in the current. It's not exactly linear, but if this perturbation is small, you can approximate it as linear. And again, the slope of this line, again, is called transconductance. It's shown as GM. It's defined as 1 over Rm equals GM. Again, exactly parallel, right? DID, dVGS, which is going to be now what? So now you can see that the expression matters, right? Because that was an exponential, we got something. So now for this expression, if we differentiate this one, if we just ignore that for now, what do we get? The transconductance of a long channel device or non-velocity saturated device. It's basically the derivative of that. So if you ignore that, it basically, this 2 cancels this 2. You get basically mu n C ox W over L VGS minus VT. Okay, so this is expressed in terms of delta VGS. You can see it's proportional. So the transconductance in the quadratic mode is proportional to the gate overdrive. Okay? But you say, wait a second, but that's in terms of voltage, this is in terms of current. Well, you can write it in terms of current if you want. Again, if you ignore that one, you can solve for delta VGS from this in terms of ID and plug it in. And when you do that, it's very straightforward to see. It becomes 2 mu n C ox W over L ID. So that's the long channel transconductance. And then we can do the short channel transconductance too. I mean, it would be derivative of this, which you can basically see it becomes this guy. It just cancels that, right? Because you differentiate it, you're left with this. So in the velocity saturated, deep velocity saturated case, so I should say deep velocity saturated case, it would be just this expression. So now you can see it doesn't even depend in deep velocity saturation on the VGS. So the operation point is not important because you're already velocity saturated. So transconductance is fixed by the maximum velocity, the saturated velocity or the saturation field that you can get. So beyond a certain point, if you get more overdrive onto it, you're not going to get more bang for your buck. You're not going to get anything. You're saturated in terms of transconductance. And now let's do some numbers. And these numbers are important because it puts things in perspective as far as the comparison of these two kinds of devices are concerned. And you may say, you said 99% or more than 99% of the transistors in use today are MOSFETs. Why are we even talking about bipolars? Well, first of all, we're not talking about today. Your training is for tomorrow. So you need to know all devices, every device. Devices that are not invented yet, you need to invent them. So anyway, but here's the thing. So let's do the numbers. So a good number for mu n C ox for an MFET is 50 microvolts. 50 microamps per volt squared. So let's start with that, and that comes from calculation of mobility and gate oxide, and it changes. It can be higher, lower, etc. Factor of 2 doesn't matter. Look, we just want to get order of magnitude calculation. So let's put that in there. And let's try to do something. Let's use this expression and try to find what W over L I would need to get 40 millisiemens for 1 milliamp. So what we are trying to do is that we are trying to make this 40 millisiemens, like that of the bipolar. Okay? And basically get with 1 milliamp, and solve for W over L. So the unknown would be the W over L. So we can do that. You can say, okay, GM is 40 millisiemens, so it's 4 times 10 to the minus 2 squared. So it would be millisiemens Siemens squared. And here you have 2 times that, so you get basically 100 microamps. So that's 10 to the minus 4. Microamps per volt squared, And then you have here, which is basically 1 milliamp times W over L. So you do this calculation, you get 1.6 10 to the minus 5 here. You get 10 to the minus 7 from there. So that's your W over L. So what do we get? Did I miss anything? No, wait a second. This is the minus 3, not 5. Right? Because that would be 16 times minus 2, so it would be negative 3. So it becomes 1.6 10 to the 4, or 16,000. So that means that for your transistor, for this guy, to have the same GM at the same current, operation current, bias current, as this guy, it needs to have a ratio of W over L. So you remember, this is L, this is W, of 16,000. Of course, you don't make it out of one incredibly long and thin finger. This is we make them out of multiple fingers, so you can actually make multiple fingers. But that's still a lot. And if you think about it, what is happening at that point? If I ask you, okay, so at that point, what is the gate overdrive? If you look at it, since this number is large, right, this number has to be very small. So essentially, you are getting into subthreshold. And we saw that in subthreshold, MOSFET behaves like has an exponential behavior, and behaves like a bipolar. So the only way you can get to those kind of transconductances is by operating in a subthreshold. And that you will see will have an impact on the maximum intrinsic gain that you get out of a transistor. And those kind of things. So this is a much beefier, much bulkier device. This is a much more powerful device. It's power hungry, but if you want to drive, this is a very powerful driver. Now, it doesn't mean that you can't do stuff with MOSFET, but it means that you have to do it in certain ways or certain impedance levels, and that's where a lot of innovation comes in. You coming up with ways of using MOSFETs that people 20 years ago, 10 years ago, did not think was possible. They said, oh, the only way you can do this or X or Y is with bipolars. And then people came up with ways of using these. But this is the basic problem that you're trying to overcome. And it really eventually boils down to impedances. A lot of those solutions boil down to the drive point impedances and controlling that and coming up with structures that would allow you to use the appropriate impedances, either lower or higher, probably most of the time lower impedances, without diminishing the fundamental operation of the system. And we'll see examples of this as we go forward. Now, one last thing, again, to make the parallel complete. If you have a PFET, you have the VDD. Oh, this should be actually VC. Well, no, that was correct. That was VDD too. They're both FETs. VDD. And then you go, so you have a VGS here, VSG really here, and then you have an ID going to ground. Okay, any questions on this? Yes?
So you said that GM is sort of the main thing that we care about, and you also said that BJTs are a lot beefier, but that most devices use MOSFETs. Why would you use MOSFETs if BJTs are
Okay. That's a great question. So the question is, again, for me to repeat it, make sure that everyone understands. I said that this is a beefier, you get more GM from this device, typically, for a typical device, than this device. And therefore, this looks like a better device. Why do people use this to begin with? Why are 99% of the transistors like that, while it appears that, at least based on this analysis, that this is the preferred device? So that's a great question. So let's see if we can take it. Are there any guesses on that before I kind of say my answer to that? But any thoughts? Yes.
Easier to fabricate MOSFETs that are really tiny scale?
So the answer, this answer is that it's easier to fabricate MOSFETs on tiny scales. At some point in time, it was, but nowadays the MOSFETs that we make are definitely not less complex. And they're practically more complex. But at some point it was. But that was not the driving point for this. there's something really great about MOSFETs that is kind of on this whiteboard that we kind of like I swept under the carpet when I was talking about. There are really two great things about them, but yes, go ahead.
Small gate current.
Small gate current, that's one, right? So you don't need to provide that gate current, and you will see that that kind of matters. There's also another thing that really matters about MOSFETs, and it helps significantly, is that turning MOSFETs on and off is equally easy. Now, if you try to drive this transistor, if this transistor is going to saturation, which is equivalent of the triode region of this thing, more or less, there's something fundamentally different about these things. So that's really deep, and we'll talk about it right now, is think about what happens when you go into saturation. Think about the device physics. And that's why we need to understand the device physics. Both junctions are forward biased, right? So both emitter and collector are injecting, in the case of an NPN, let's say, electrons into the base. And remember, electrons are minority charge carriers, right? Now, the difference between these guys can be expressed in this form, and I will articulate it. This is a minority charge carrier controlled, and this is a majority charge carrier controlled device. One way to think about it. Now, what happens if you inject a ton of minority charges into the base? Now, fine, you're just drawing current, et cetera, but when you try to turn it off, when you remove the voltages, where does this minority charge carrier go? It will take a long time for it to recombine, right? Because recombination is a slow process. So all it can do is to end up in the collector. Just every so often, some of them get to the collector and just going to go in the collector. So you try to turn the transistor off, you remove the voltage, but the collector current keeps going and going and going, and it doesn't turn off. Because all that minority charge carrier, most of it needs to go into the collector. And it does not turn off easily. So making logic gates for these things, the way we make it with MOS transistors, is hard, because with MOS transistor, we just let them go into the triode region. Fine. They still go into the drain and source. They were majority charge carriers anyway. Now, so essentially, making switching gates out of these guys is harder. Now, in fact, still you can make really fast switching pairs with this. It's called ECL, with differential pairs, so that they don't go into saturation. But they are very power hungry because they have current consumption when they are not switching, because it's a differential pair that's constantly drawing current. Now, that's deadly if you're making a microprocessor. Why is it deadly? Because you don't make a microprocessor with one or two gates. You make it with hundreds of millions of gates. And if each one of your gates has static current, that's going to make it impossible from power consumption and thermal perspective to make. So that's why what you do is that instead of that, you come and create, so with these guys, you can make the MOS gate, which we haven't talked about, but you're probably familiar with. You can have an NMOS and a PMOS, and at least in the basic model, you're drawing no current here, and then when the gate is not switching, there's no current here. So there's no static current. And since most of the transistors that are used in digital circuitry, hence most of the transistors that are used happen to be of this kind, not that kind. Now, that business of minority charge carrier and majority charge carrier becomes a little bit blurry as you go to very small dimension devices and all those things, because their behavior, there are some elements of the behavior that's controlled by both of them. So that is not completely and entirely true anymore, but there's a way to think about it. All right, great question. Any other questions? Yes?
What's the frequency difference between BJT and MOS?
Okay, now we'll get to that. Actually, that will be one of the things that we'll analyze, the frequency behavior, the high frequency behavior, what determines that. But before we, so since you asked a question now, let's see what are the parameters, and we'll do it quantitatively in a few minutes. But in terms of frequency behavior, what are the two things that determine, we talked about this before, right? What determines the speed of something? Your force and its inertia. The current and the capacitor. Often. I mean, there are other combinations in electrical engineering. And it's not exactly right. There are some subtleties to this that, as we'll see later on when we talk about the so your driving force and your capacitance. So now, here's a question. This is the driving force, right? This is the driving force, right? This is the drive. GN, transconductance, is the driving force. So think about it this way. If I wanted to make this for the same dimensions of these things, if at the very basic level, the driving force of these two are not the same, or if you try to make them the same, your W over L becomes pretty large. What was the capacitance, roughly, if you think about the gate capacitance? What was the expression for it? You had the gate capacitance. It was the area of the gate would determine the capacitance. So the area is W times L. And your L can be at a minimum, so the capacitance can be larger. So again, intrinsically, the frequency behavior of these guys is better than these guys. Because for the same transconductance, you will have more capacitance. Or for the same capacitance, you will have less transconductance. But people, the MOS transistor, this ability to make this kind of gate is so important that people have come up with a lot of creative ways to fix some of these problems. And they're close. They're not order of magnitude difference, the best bipolar. But still, the best bipolars are faster, generally speaking. OK, so that's for that. Let's continue briefly. You know what? Let's take a break. And then when we come back, we develop all of those other parasitic elements, the rest of the model for this thing. And then we'll use that for our analysis going forward. Any questions?